physics test was so bad that he said we literally couldn't come back from it and that we would just be in the hole forever. And so he's letting us retake the exact same test on Monday.
Okay. So what you're saying is it's a chance. Yeah. You're the worst set of students I've ever had in my entire life. Now,
You heard that too?
now go take this test again. Okay. What was the subject of the test?
It's just like the first 3 chapters, like remembering
I don't know
math,
what the first 3 chapters of the test are.
displacement, velocity, acceleration, and 2 directions.
Okay. Now, this is going to sound like a joke, like I am joking, but I did statistics tracking of the Chemistry 1 exam that I gave in the summer. The lowest scoring question on the test was the first question on the test. Only 16% of the students got it right. And it was, add these 2 numbers together.
The easiest questions are always the hardest because people overthink it.
Add these 2 numbers together.
Yeah, no, I would have found a way to get it wrong. I know.
Yeah, I would have divided them. If you didn't say
16% of the
add
class.
them,
Like legit, in my math problem, like that I do in class, it's a complicated problem, but I only miss it because of one simple little thing. Like, I forgot to put a negative.
They got the tough questions. Okay, they just did the easy stuff.
as a teacher, like how does that make you feel? Like, do you feel like you prepared them, or what is your thoughts when you see that?
I had adequately prepared them to add 2 numbers together. No, if I ask a question and some people get it wrong, some people get it right, then it is what it is. If I ask a question and everybody gets it wrong, then that's my fault. Unless the question is, add these 2 numbers together. Okay, time to move on. This is a chirality center. 4 different groups around a tetrahedral carbon. This is a chirality center. I haven't looked, I just made these at random. There's a black, gray, a red, and a blue. This and this might be the same as each other, or might not. The way that we check is to make things line up, and if they all line up, hey, these 2 molecules are the same as each other. Okay, so these are the same, which means that the mirror images are not the same. Right? Okay. What if I had a molecule that looked like this? This now has 2 chirality centers. In fact, what we could do is cut out the middleman. Let's do some creative accounting. Even simpler. Now I only have 2 carbons. I don't have the one in the middle. I have 2 carbons. This carbon is chiral. It has a blue, a gray, a red, and a black. This carbon is chiral. It has a blue, a gray, a red, and a black. This might be an R, or it might be an S. This might be an R, or it might be an S. With 1 chirality center, your options are you're either an R or an S. With 2 chirality centers, how many options do I have? I have 4. This could be RR. It could be SS. It could be RS, or it could be SR. If I threw another chirality center in there, how many do you think that's going to generate? If I have 1 chirality center, 2 raised to the power of 1 is 2. I have 2 stereoisomers. I have the R and the S. If I have 2 chirality centers, it's 2 to the power of 2, which is 4. 2 squared is 4. I have 4 chirality centers. I have the RR, the RS, the SR, and the SS. If I have 3 chirality centers, how many isomers do I generate? 8. And if I have 4 chirality centers, 16. This little molecule right here. That's glucose, C6H12O6. Glucose, C6H12O6, is part of a family of stereoisomers. It has 15 siblings. There are 15 ways of writing C6H12O6, and them all being in this family, all being aldohexose carbohydrates. So this is going to start to get out of hand. We're only going to talk about small molecules, so we'll deal with it. Today we'll do this part right here. We're going to look at molecules with 2 chirality centers. This is a Fischer projection. In a Fischer projection, when you have multiple chirality centers, we stack them on top of each other. We don't write them horizontally, we write them vertically. This has an unforeseen downside. Can anybody see the bad thing that might be generated by us stacking our chirality centers in a Fischer projection on top of each other? The bond of lowest priority is never going to point away from us. The horizontal bonds always point towards you in a Fischer projection. So in these molecules, I'm going to do a whole chapter on this molecule. And I'm not kidding. In Organic 2, there is an entire chapter on this. Every hydrogen is in the wrong place. So if you want to figure out what the configuration is, you still obey the rules, but then you reverse your answer. Okay, it's just a complicating factor. Be ready for it. Okay, let's make something up. I have two carbons. They're bonded to each other. And I'm going to put 4 different groups around the carbon on the left and on the carbon on the right. Okay, shout them out.
LH. Right. Chlorine.
Okay.
Nitrogen.
Ooh, that's mean. And let's put a methyl. Okay. This has got multiple functional groups because there are lone pairs in here. So this one's going to be a bit of a bear if you wanted to name it. I would probably name the amine and call that a hydroxy group, so chloro hydroxyamine. Okay. Is it just me, or did the camera get a little bit fuzzy? Sometimes if I walk in front of it too much, it tries to focus on the object in the front and usually zoom out and zoom back in again. Is that better? Yeah. All right. We have 3 carbons. If I make this carbon number 1, then that's 2 and that's 3, and I've got substituents at 2 and 3. Or I make this carbon number 1, and then I have substituents at 1 and 2. So let's make this 1. Okay. So that's carbon number 1. And this is carbon number 2. And carbon number 1 is chiral. There's 4 different groups around it. And carbon number 2 is also chiral. But carbon number 3 isn't. Carbon number 3 is methyl. There's 3 hydrogens. So it's not. All right, so your test split into 2 parts as multiple choice test, and then there's a worksheet. One of the questions on that worksheet is, here's a molecule. I've even written the condensed structure out, condensed formula out for you. Show it to me as Fisher projections and show me all the possibilities. When the question is worded that way, you have complete free reign of where to start. So here's carbon number 1. We're going to write a Fisher projection. What do you want to go here? Here are our choices: hydrogen, chlorine, hydroxy, or this part. In fact, that part's not a choice because it's here. So I've got these 3 open spaces. Let's put those in. If you put the hydrogen on a vertical position, the bond of lowest priority is pointing away from you. So if the question asks you to identify the R or S at any of these places, you just made your life easier. If you didn't do it, no biggie. because we can fix that. That means that the chloro goes here, and then this is carbon number 2, and it has a hydrogen, an amine, and a methyl. Okay, what goes here? What goes there? Which gin?
Nitrogen.
Nitrogen. It's difficult with the mouse card. Oh, that's a 2. It's a 2, 2. Again, that puts your hydrogen, your bond of lowest priority, on a vertical position. So now we could figure out what the configuration of both of these are. So for the red one, I have 4 groups. I have a chloro. Ooh. Chloro's a 35. I have an oxygen, that's a 16. I have a hydrogen that's 1, and I have a carbon that's 12. So 35 to 16 to 12. 35 to 16 to 12. R or S? That's S, going counterclockwise. And because our bond of lowest priority is pointing away from us, we got it right.
Can you explain what's 12?
There's a carbon there. Carbon has an atomic mass of 12.
Oh, so you
Chlorine
just-
has an atomic mass of 35. Oxygen has an atomic mass of 16. Hydrogen has an atomic mass of 1. We identify the atomic mass of the atoms directly attached to the chirality center, and then we prioritize them in descending mass. Heaviest, next heaviest, next heaviest, with the lightest one pointing away from us. Okay, let's do this for carbon number 2. Carbon number 2 has a nitrogen. That's a 14. It has a hydrogen. That's a 1. It has a carbon. That's a 12. And then it has another carbon here. That's a 12. These two are in a tie. This carbon is only attached to hydrogens, which are only worth 1. But this carbon is attached to a chlorine, which is worth 35, and it's attached to an oxygen, which is worth 16. So my priority goes 1 to 2 to 3. It goes that way. So this is also the S. This decreasing priority is something called the Cahn-Ingold Prelog rule. CIP. You ever see it written down as, tell me what the CIP rule is for this molecule? It means tell me the priorities. Cahn-Ingold Prelog. Okay, so we have drawn our first molecule as a Fischer projection that has 2 chirality centers. How many more to go? 3. There are 3 missing isomers. Here's how we do that. Let's call this one A. So what you do when you're given free rein to write a molecule like this is you take your time and you do A correctly. You make sure that you've got all the attachments right, that you don't rush this and add a carbon where there's not supposed to be a carbon, lose a carbon where there's not supposed to be a carbon. You transcribe the molecule correctly, which is why I always start with the Kekule structure. I always write the structure out first before I turn it into a Fisher projection. Then you make sure that you identify the stereochemical configuration of this first one, and you take your time to do it right. Because what we're going to do next is find the enantiomer of A. An enantiomer is just the mirror image. So draw the mirror image of A. The mirror image of A is still two Fisher projections stacked on top of each other. Whatever is closest to the mirror is reflected first. Whatever is furthest away from the mirror is reflected last. Now, am I going to ask you to calculate the configuration, stereochemical configuration at these sites again? No, because you took your time and you did it right the first time. What's the opposite of S? What's the mirror image of S? R. And what's the mirror image of S? It's another R. So this was the SS isomer, and we would actually call that 1S, 2S. So this gets to be 1R, 2R. That would be the name of our isomer. All right, that's A and B. There's still two more isomers left. To get to isomer C, what we're going to do is look at this first molecule, leave one of the chirality centers alone. I usually leave the bottom one alone, but there's no rule that says it has to do that. Leave one of these alone and flip the other one. Now, to flip the chirality center of a Fisher projection, all you have to do is exchange any two groups. So you could switch the alcohol for the hydrogen, you could switch the hydrogen for the chlorine, but the most obvious to the human eye is if you switch these two on the horizontal. Your eye is going to be able to catch that. So let's switch those, which means they're the same as this, but keep these two original ones. Okay, so this is not the SS and it is not the RR. This is now RS. Guess what the missing isomer is? Yeah, try it. So I've got the 1S. Oh. Now draw the mirror image of C. The mirror image of C gives you D. Oh, I'm off screen, right? Here's what I'm going to do. I'm going to squeeze this in so I can get everything on screen for those watching at home. Flip the top. Move the bottom where it is. Okay. So this is C, and C is the 1R to S. And then I just take the mirror image of C to give me D. I'm probably going to have to move the camera anyway, people at home. Bear with me. And this is the opposite of what we already have. So this is the R, that is the S. This is the S, and this is the R. So this gets to be 1S to R. Okay? Let me just move over a bit. That should do it. Can you see everything on the screen at home? I think I've got it all in. Okay. All right. A and B are mirror images. And we already know that the R and the S, when they're a mirror image, don't superimpose. So these two don't superimpose. So the relationship between A and B are enantiomers. Anything else on the board that's obviously an enantiomer? C and D are also enantiomers. Now, what about A
Oh,
and
wait, I meant to say, oh, never mind.
yeah?
I said it wrong.
What about these two, B and C? They're next to each other. Are they mirror images of each other? No, they're not. They're not. But they are still stereoisomers. I've got retention between these two chirality sensors, but inversion here. So let's look. A and C are different at one of the chirality sensors. A and D are different at one of the chirality sensors. B and C are different at one of the chirality sensors. B and D are different at one of the chirality sensors. So our relationship between A and C and A and D and B and C and B and D are something different, something we haven't seen before. These are diastereoisomers. And a diastereoisomer is different at one of multiple chirality centers. Now, I did say that we're going to come back to this at the end of Organic 2 and look at glucose and carbohydrates. And when we do, and we look at molecules that have lots of chirality in them, we're going to add an additional word to this. So this definition of being different at one chirality center is going to hold you good for about the next 20 weeks. And then we're going to add an extra word to it for different cases, okay? There's another word coming. This will do for us for right now. Okay. Let's do it again. Let's do it again. Am I erased the board? People playing at home? That's a yes. Now I did realize last night, well, so I wrote the test and I added a question in there, but I figured, oh, we'll get to that today. And then today I realized I really don't even want to cover that topic, but I haven't changed the test. So there is a question on the test that we haven't learned yet. And I'm not going to bother. So everybody's in the same boat. So when you get to that one question that is like, what the, yeah. That means, you know, I'm going to round that question up. Okay, so don't stress about it. You'll know it when you see it. So this is the example we did in lab, I believe, butanediol, right? Let's change that. Or do you want it to be the same? Let's do it the same. Because you haven't written your lab report yet. And what I'm about to do is show you how to write the answer to the lab report. This is butanediol with the diols at the 2 and the 3. This is, I've already written my lab report. What does this say? Can you move the camera a little bit up? Yeah, absolutely. You're gonna have to tell me when I'm doing it right, because we kind of can't see our own camera. It gives us such a small box. Okay, great. This is 2,3-butane-diol. And that's a chirality center. It's a hydrogen, a methyl, an alcohol, and then a 2-carbon chain. And that's a chirality center. So what if the question were, draw all the possible stereoisomers for 2,3-butane-diol as Fischer projections? 2 chirality centers generates me 4 isomers. So now I actually know what to do. I'm going to draw my 4 skeletons for the Fischer projection. I can even call these A and B and C and D, although, you know, you don't have to. And then I'm just going to fill stuff in. So go ahead and start filling stuff in. You want to do A the best way that you possibly can. And then you want to make B the mirror image of A. And then you want to make C the same bottom as A, but a different top. And then you make D be the mirror image of C. And given complete free rein in a question like this, you draw the molecule out first, because this could be given to you only as a name. You draw the molecule out and you realize there's a hydrogen there. That's definitely going to be the bond of lowest priority. I could opt to put it here. I could. And in fact, I'm going to. Because I'm going to do it wrong on purpose. Look at me, spiteful. Putting the bonds of lowest priority in the wrong place. Because it makes my molecule look prettier with all the carbons in a row, right? A and B are mirror images of each other. A and C share the same bottom part, but a different top. So keep the bottom the same and switch the top. And then D is the mirror image of C. Now, whatever you wrote down, continue writing that. I mean, don't erase a good answer just because a bad answer showed up in front of you. Like, do what's the smart thing to do. Okay. Now, I have to prioritize using my Kahn-Ingold pre-log rules. What's going on here? Oxygen is a 16, carbon is a 12, hydrogen is a 1, carbon is a 12. This carbon is higher in priority than that carbon, because that's a methyl. This carbon is attached to this oxygen. So my priorities here are 1 and 2 and 3. So 1 and 2 and 3 is clockwise. So is that the R or the S, because it's going clockwise? That's the S, because that hydrogen is pointing towards you. So it looks like an R, but actually is the S. And when I look at this carbon, this has a 16, that's going to be my winner, a carbon that's a 12, and a carbon that's a 12. This is my winner, that's my number 2, this is my number 3. And 1 to 2 to 3 looks counterclockwise. Counterclockwise should be an S. But I drew my molecule wrong, because both of those hydrogens are on horizontal positions. And if you put the bond of lowest priority on a fission projection on a horizontal position, it's wrong. So it is not the S, it is the R. So this is my 2S3R isomer. And now I know what they are for all of them. Because if this is 2S3R, then this is 2R3S. And that makes this one that is same at the bottom, but different at the top. There you go. Take your time to do it right once. You don't have to do the priorities for all of them. Just take your time, do it right once, and then use logic to figure out what everything else is. Okay. What's the relationship between A and B? They're enantiomers. They're mirror images. And the relationship between C and D are enantiomers. And the relationship between B and C and B and D and A and C and A and D, these are all diastereoisomers. So nothing new here, nothing to see, nothing could possibly go wrong. Everything looks good. Or is it? So your exam goes live at 11 a.m. It is available over the entirety of the weekend. Closes Sunday night at 11:59 p.m. That is not permission for you to start attempting the test at 11:15 p.m. on a Sunday. Okay. Make sure that you have sufficient alone time, uninterrupted, to complete the test, because you're going to get one shot at it. Okay. You take the test whenever you feel like, but once you start, you must complete the test. You are not going to be allowed to get up, walk away, and pause the test, because that's when it starts, is that right? When does that start? We wouldn't want to miss the premiere of Dancing with the Stars because chemistry exam. Carol Baskin's on this year. She totally did not kill her husband. Carol Baskin is famous for not killing her husband. That's a great show. That's a great show. Yes, I'm still here. I'm slightly off camera because I'm building models. What does this say? Oh, 100%. I would like to say for the record that Haley's opinion is that of Haley alone and does not reflect that of faculty, staff, and administration of Concordia University, Texas. Carol Baskin is very highly litigious. She's known for two things, for being litigious and for not killing her husband. Also has sweet dance moves. That's three things. Okay. This is 2,3-butanediol. Black atoms are carbons, red atoms are oxygens, gray ones can be hydrogens. This is 2,3-butanediol also. Now, these, it turns out, quite by accident, are different from each other. But see how this side agrees and that side doesn't? I have two chirality centers, and these differ at one of those chirality centers, which makes these two molecules diastereoisomers. The relationship between these two is that they're diastereoisomers. So let's look at that one. And take the mirror image of that, which means doing this. Switching any two groups changes the configuration. These are mirror images of one another. And in fact, what we would do, look, hydrogens pointing out towards you, red oxygens pointing out towards you, the black vertical bonds being the carbons pointing away. These are mirror images of one another. These are enantiomers. But if I were to do something, unfortunately, like dropping them to the floor and then picking them back up again, I wouldn't be able to tell which one was which. Hold on. Because these two, make it happen, come on, are the same as each other. Which is going to make me rethink my initial statement. That A and B are not enantiomers. They're the same as each other. How did that happen? It happened because this molecule is its own mirror image. This side of the molecule is the same as that side of the molecule, which means this molecule has a plane of symmetry. It is a mirror plane, all of its own. And when you reflect any shape that has reflective geometry like this, symmetry, then its reflection is itself. So this is the reflection of that. Turns out to be the same thing. We're going to call those meso. Meso means, yes, that is the S, and that is the R, and that is the R, and that is the S. But because they have a plane of symmetry, it goes away. These are meso. They're the same as each other. Now, does that mean that my other two, that C and D, are also not enantiomers? Okay, let's figure that out. These are mirror images of one another. Yeah? Okay, let's see if we can match it up to what's on the board. With the black atoms pointing away from us, the oxygen pointing towards us here, and the oxygen pointing towards us there. Okay, so that's this one. And then hydrogen, black, gray. This is the other one. Okay. Just bring that out a little bit. These two are mirror images of each other. Nothing I do can make them overlap. These truly are enantiomers. And they get to stay enantiomers Because if I look at any individual isomer, it has no symmetry. These are different. There's no symmetry here. Okay. So A and B get to be meso, the same as each other, because of the symmetry that runs right through the middle of this. Okay? This, a long line with a little dash and a long line, that's a plane of symmetry. That's a mirror plane right there. These are symmetrical. And if you're symmetrical, your mirror image is yourself. C and D remain enantiomers. B and C, B and D, A and C, and A and D remain as diastereoisomers. Okay? So the question that is on the test that we didn't get to is about E and Z notation in alkenes. And I'm just going to leave it on the test. I'm going to leave it on the, I mean, I could go back and change it, but there's something with the technology that if you deploy a test and then you change it, it kind of jeopardizes that the test runs smoothly. And these tests ran anything but smoothly earlier in the week. So I'm not going to jeopardize it. Everybody can flunk that question. I don't care. Okay, I'm going to round that question up. All right, questions? You have until Sunday night to complete both parts of the test. Go to the assignments folder in Blackboard. Part 1 is the multiple choice quiz, 30 questions. Part 2 is a written take-home worksheet that you then take home, scribble your answer on it, photograph it, scan it, send it back into the assignment link as a PDF or a JPEG or a Word document, but not something other than those 3. Blackboard won't be able to read it. I won't be able to grade it. The second part of the test, when you open it, will be apparent what its purpose is. They're all questions about sketching. Okay? Because I cannot test your ability to sketch by doing a multiple choice quiz. Okay? Anything you need to know, shoot me an email. It is the weekend. Don't expect an immediate response, but we'll deal with it. Okay? All right, off you go. Okay. 2 down, 1 to go. Okay.
Can we use like a piece of paper for like the
Yeah.
multiple choice to?
Yeah, so it'll ask you at the beginning to show your surroundings. If you hold up a piece of paper and you show me front and back that it's clear, that's absolutely fine.
Okay.
Absolutely.
Thank you.
I'm gonna be like, I might need to.
Yeah, I know, all my homework and stuff I'm working on,